So our next speaker is Tero Heikkilä from University of Jyväskylä in Finland. I hope I pronounced that correctly.
Okay.
And he will be talking about flat bands in graphene-based systems. So Tero, please, the 30 minutes are all yours now.
Thank you, Alexei, and thanks a lot for inviting me to this very interesting meeting. I will talk about a topic that has been already discussed a few times today, but from maybe slightly different perspective. So, and sort of the title of my talk now is Flat Bands in Graphene-based Systems. Actually, the title that shows up in the program is contains this crystalline topological insulators as well. This is the most recent work of ours, but after assembling this talk, I realized that I won't have enough time to talk about that other part, so I will just skip it. And okay, so I advise you to look at our paper on this. The work that I'm reporting, I will tell about, has been done together with various collaborators, especially Grisha Volovic from Aalto University and the London Institute, with whom we started this work over 10 years ago, and also the previous speaker, Päivi Törmä, and students and postdocs, and Nikolai Kopnin. With him, we started the work on superconductivity. So my talk will be actually not so much about superconductivity, but actually more about different ways to get to flat bands. But I will always kind of try to motivate it from the point of view of superconductivity. So I will consider 3 different variants of sort of approximate flat bands in graphene-based systems. And this is not such a new topic for me, because already 6 years ago we proposed a project to realize this experimentally to the EU, but unfortunately we didn't get the funding. But actually, as you will hear today in my talk, majority of these proposals have been now sort of realized experimentally. Okay, already the previous talk by Päivi sort of explained a bit about superconductivity. It's sort of ordered state with a broken symmetry described by an order parameter, which is basically the pairing amplitude, so expectational value of the pair of 2 operators. And this is of course the mean field point of view to this. Okay, from the phase gradient of this order parameter, you get supercurrent characterized by the superfluid weight, which is also mentioned in Päivi's talk. Now, in my talk, the sort of my kind of approach to this is to ask how to relate the size of delta to the band structure, and I use this to get there. I used the BCS mean field theory, where this delta generally depends on the competition between an attractive interaction, which is mediated usually by a coupling to a sort of some spectrum of bosonic modes, usually phonons in conventional superconductors. And this attractive interaction has a strength lambda. And then sort of we have the electronic dispersion. Electrons which have some dispersion, they generally have some bandwidth and density of states at the Fermi energy. And then there is some characteristic frequency of these bosons which are mediating this attractive interaction. And one can study basically the mean field delta in these various systems and study how it behaves with respect to these parameters. And so first one can start from conventional metals, where the bandwidth is the largest of these energies. And then we have the let's say the bosonic energy or frequency is below that, and then superconductivity lives even on a much smaller scale. And in this case, we have this usual BCS or result where the the delta is proportional to this cutoff frequency times the exponential containing the coupling strength and the density of states. And then you have other regimes which have been also considered recently, but sort of maybe not as well known. So one is that of narrow bands. So we kind of go towards flat bands. So we basically they take a bandwidth which is smaller than this characteristic frequency of the bosons. And in this case, we get similar kind of expression as before, but then replacing this cutoff frequency by this bandwidth. In this case, typically, if you do this by shrinking your band smaller, your density of states becomes also larger, which then means that your delta and T's are typically larger than in the previous case. Okay, and then there is the extreme limit of flat bands where the bandwidth is small compared to even the size of the superconducting order parameter. It's of course a self-consistent condition that you have to check. In this case, the delta is actually linearly proportional to this interaction strength. And sort of interestingly, as you can also see in the previous settings, that the density of states actually it's an intensive property. So its dimension is 1 over energy, 1 over sort of length to the power d, where d is dimension, which means that this lambda also has to have a dimension of energy times sort of meter to the dimension. And therefore, in order to get an energy from here, you have to actually multiply this constant by another constant, which is in this flat band limit, it's the size of the flat band in momentum space. So yeah, okay, so basically what you get is this linear scaling with between delta and the interaction strength, but you also get this flat band size as a parameter of your model. And this is kind of the aspect from which I want to sort of approach the different flat bands in my talk today. So then the natural question is basically what determines the size of the flat band and how to maybe maximize it in systems that you might be considering in experiments. In this case, I focus on graphene-based systems. There are, of course, several caveats to my argument which is based on mean field model. So the validity of the mean field theory, the validity of the mere electron phonon model, and especially the Migdal theorem is actually questionable in flat bands. And of course the fact that there can be also other correlated states like people have considered magnetism, but also you could have spin density waves or charge density waves appearing due to interaction. But here I just look at if there is superconductivity, how does it behave? Okay, so my kind of task in today's talk is to construct different approximate flat band models from graphene. And what I basically mean by approximate flat bands is that there can be finite dispersion, but it is in some sense small. Okay, so I presume that you all know graphene, so hexagonal lattice of carbon atoms whose electronic dispersion contains this sort of pair of valleys. So where there is a band touching point where the sort of the Hamiltonian can be expressed in terms of the Dirac 2D Dirac Hamiltonian, which is just sigma dot p here. So and this valley is also sort of arranged in this kind of a hexagonal structure, which is just a rotated hexagon from the real space hexagon. Now, sort of the Dirac point is maybe the furthest away from flat band system. It has a flat band has a diverging density of states. Dirac point has a zero density of states. But sort of construct from Dirac point, you can construct system that has these approximate flat bands. And the three sort of systems that I will consider here are that of stacked graphene, so actually towards graphite, periodically strained graphene, and twisted bilayer graphene. And let's start from stacked graphene. So what happens if you put two graphene layers on top of each other? The energetically sort of favorable configuration is not the one where the honeycomb lattices are exactly on top of each other, but rather actually where they are sort of shifted or rotated with respect to each other, so that the sort of one pair of atoms, let's say the blue and the underlying red atom. Okay, I should have gone the other direction. Sorry. Oh wow. Okay, so yeah, so the one pair of atoms is on top of each other, and then sort of one atom is on top of the hexagon on both lattices. And this is how you construct always every pair of graphene layers. And then if you just have a single pair, you have bilayer graphene. And as is quite well known in this case, from the Dirac spectrum, you go to this semi-metal with quadratic touching, at least in a certain approximative model. Now, if you want to continue the stacking of sort of Dirac points, you go, of course, to graphite, and there are two extreme versions of graphite stacking. There is the so-called Bernal graphite, which is the stable, sort of the most stable configuration, and then there is a metastable rhombohedral configuration, where every pair of layers always has the same Bernal stacking that I showed before, but which atoms are on top of each other changes. And actually, both of these graphites are very interesting nodal line semi-metals. I will not talk about too much the Bernal graphite, but actually about rhombohedral graphite, which has a flat band on top and bottom surfaces. But let's say if you want to make a model of this, the easiest way is to look at what happens if you have just Dirac points, several Dirac points, and then you start stacking them by coupling sort of pairs of atoms. So, and you kind of make the rule where you always couple one blue atom to one red atom, so 1A to 1B atom in the sublattice in one way or another, and then if you make kind of this always the different atom couples sort of with strong coupling, you have rhombohedral stacking. If you have this zigzag pattern here, you have Bernal stacking. And the size of the coupling is called gamma 1. It has a sort of typical size range is around 0.3 electron volts in graphite, which corresponds to around 3,500 Kelvin in temperature units. Okay, if you look at now a rhombohedral multilayer, you can very easily make a model of this and study the spectrum. What you find out is actually that it has a low energy spectrum that is that has a sort of approximate flat band. Basically, the idea is that if you stack these layers, you notice that always the top and bottom layer have a single uncoupled sort of lattice side. This coupled lattice side is sort of uncoupled only at zero momentum. If you put a finite transverse momentum, there is a coupling, but actually this coupling then will just sort of kind of delocalize the state up to a certain amount. That depends on the size of this coupling with respect to this coupling's size of the momentum with respect to the coupling gamma 1. And yeah, so you have this sort of surface states, and they have the dispersion, which goes like roughly it goes like p to the nth power, where n is the number of layers. So if you now make a very large n, you have a flat band. The size of the flat band in this case is given by the size of this coupling, gamma 1, and the scale comes from the Fermi velocity in the single layer. You can argue the presence of this flat band from bulk rhombohedral graphite. If you write now the Hamiltonian full bulk rhombohedral graphite in this approximation, you find out that actually it contains a spiral nodal line. So there is a sort of line of band crossings which form these spirals, and actually at every sort of valley there is a single spiral. And then the spiral has a topological charge, which is basically the spiral helicity. And when you project the spiral to the surface, you have a region of sort of zero energy region. And this is basically the flat band. Yeah, so this is of course, yeah, so this is the normal state. Then you can consider what happens if you add this attractive interaction and solve, for example, Bogoliubov-Duchenne equations to find out a mean field Euler parameter and also the position dependence of it. What you find out is that the Euler parameter peaks at the surfaces. So you have surface superconductivity, whose range depends on the sort of ratio of the coupling strength and the this Hoping strength. You can then study also, let's say, that this mean field equation, what happens to delta with respect to the spectrum with a finite n. You can actually solve this analytically, but the result is a bit complicated, so I will not go too much into detail. But the bottom line is that if you take a large number of layers, you get a linear scaling between delta and the coupling strength, which is now here G. But and the size of the flat band then appears. So it's this flat band squared. You can study the dependence on doping, for example. You can show that it destroys surface superconductivity for certain critical doping and so on. Now, what I presented you before was based on a model where I only take this strongest coupling between the layers, this gamma 1 coupling. In reality, there are also other couplings denoted here, gamma 3, gamma 4, and so on. Or you can study also, we have made a DFT study of the surface spectrum. And what we find out is that you still have a surface state in the presence of these other couplings, but actually instead of a flat band, you have a quadratic dispersion. And so which means that you essentially have a narrow band. And this is because these other couplings, especially the gamma 4, they break the chiral symmetry of the Hamiltonian and result actually, instead of the flat band, to this drumhead surface states in this kind of nodal line. Nevertheless, it's a sort of almost flat or very, very narrow band in this case. Now, experimental progress about possibility of superconductivity in this system, there actually has been quite recent work on this by the group of Andrea Young. They studied the trilayer graphene rhombohedrally stacked trilayer, and they found out sort of this is the phase diagram between of the linear resistance with respect to the charge density, and then a sort of internal electric field between the layers. And they find out these superconducting cones, which are quite interesting. The only thing is that this is nowhere near room temperature superconductivity. The Brzezinski-Kostelis-Tallis transition temperature in those systems was 100 millikelvin. But at least we can directly use the previous results to predict that if you would go to a sort of larger number of layers, so let's say 4 or 5, you would get a much higher TC. And actually also what one also finds that these results are consistent with surface superconductivity, that where the sort of superconductivity only depends on the potential that is the sum of the sort of average potential plus the plus this d here. I will not go to too much detail, but basically that's the message. In fact, you could realize also superconductivity in such systems not as a surface state, but as a kind of thin boundary state. So if you have rhombohedral stacking and then you make a stacking fault, you would have also a localized state there, and you could study what happens to superconductivity there. There is some evidence that maybe of possible superconductivity in such sort of systems where you have some stacking faults. This is work from 2013 already from Leipzig, where they actually found a resistance transition in such graphite systems at up to 175 Kelvin, or this is maybe 150 or so. This is a lot on log scale, so it depends on where you exactly put the transition temperature. The problem here was that they did not know the structure of the system so well, so it is not very easy to make any theory on this, and then also sort of between different samples there was a big variation. Okay, so but the bottom line was that the stacked graphene can have flat bands, which sort of whose size scales with this gamma 1 coupling. Now, we have also considered other types of flat bands. So the next topic is the periodically strained graphene, which and how does this work? So now, okay, so what you can do is that you can shift sort of adiabatically the atoms in the lattice, and if the shifts are small compared to the average lattice, you can treat them as sort of from adiabatic theory, starting from the let's say ordinary Poth theorem of periodic lattices, and then studying these shifts as perturbations. And in this case, what you study is the strain field, which may consist of in-plane and out-of-plane strains, and then from those you construct this pseudo-vector potential. And then sort of this shows up in the Dirac equation by modifying it by basically in the same way as an ordinary vector potential, but in such a way that the sign of this vector potential is opposite in two different values. So in this case, this pseudo vector potential does not break the time reversal symmetry like the regular one would. Okay, now if you so what we have considered is a case where such a strain has a sort of 1D oscillation, so with some sort of amplitude beta. So for example, the strain in the y direction depends on x in a periodic fashion. And or the strain field is basically this one. This is the pseudo vector potential, and the amplitude is indeed this beta. If you consider beta that is large compared to 1, you actually get a 2D flat band in this system. This flat band is different from the previous one, which was p to the nth power. In this case, actually, this remains to be a linear. This has a linear spectrum, but in such a way that the prefactor of this linear spectrum is extremely small. So compared to the intrinsic Fermi velocity of graphene, you divide it by an exponential function. So if beta is just somewhat larger than pi, this speed becomes extremely small, and then actually you get an asymptotic flat band in this system. And we have studied, okay, yeah, and you can also argue actually the presence of this flat band in this system from the SSH model, or actually the Jaggi-Reppi model that has been presented a few times already in this meeting. sort of the way to do it is to consider kind of a 1D model where ky here is a parameter of this 1D model, and then this this maps to the Jacobi-Rapid model where the mass is just the ky, the wide ky plus then this pseudo vector potential, and this is an oscillating function. So if because it oscillates, there is actually a zero energy state at each crossing point where it changes sign due to the Jacobi-Rapid, like in the Jacobi-Rapid model, and then the flat band is actually consisting of the sort of basically the finite dispersion comes from the overlap energy between the various zero energy modes. So if ky is equal to 0, this is exact and the energy is 0, but then if you have a finite ky, there is finite overlap energy, but this overlap energy scales sort of exponentially with the amplitude of this A. We have studied what happens if you now add attractive interaction here. What you get is position dependent delta, and yeah, you can also look at, for example, the superfluid weight. It is finite, like also in the previous case. The BKT temperature is finite, and so you would expect this system to have superconductivity if there is attractive interaction. Now, yeah, so the scaling of delta versus the coupling strength is also linear here, but actually it has a quantum critical point, sort of, which just becomes smaller and smaller as you increase beta. In this case, the size of the flat band is slightly different than before, so this is now fixed by the amplitude of the strain and the period of the strain. Yeah. There is actually some there's some work where people, quite recent work from Eva Andre's group, where they studied such periodic strain profiles in graphene on kind of buccal structures on graphene membranes, and so they realized the strain superlattice. What they can see in STM is the presence of kind of lambda levels from this zero vector potential. And basically the zeroth order lambda level is the flat band that I mentioned before. But they also, in addition, they show in their the studies that the spectra depend on the filling, and this is indicative of strong interaction effects. But they haven't really reported what type of interaction effects would be present. They don't have. It's very difficult to make transport studies in these systems. Okay, my last topic, I guess I have still a little bit of time to mention it, is the twisted bilayer graphene. So another way to get flat bands from graphene is to twist it. So now, instead of going to this full Bernal stacking twist, we consider an arbitrary twist. And in this case, what you can see in such systems, if you put two graphenes on top of each other, is this moire superlattice. And sort of one way to sort of understand this moire superlattice is to take this this reciprocal lattice of graphene and sort of two of them and twist those with respect to each other, and then there is kind of a nesting vector that sort of defines another Brillouin zone for the superlattice. In fact, this only works for sort of this bilayer graphene is exactly periodic only for certain commensurate angles, but they become dense at small angles. So we kind of only concentrate on those commensurate angles. You can study the normal state spectrum as a function of the twisting, and you find out that there is this so-called magic angle at 1.08 degrees where the bandwidth becomes smallest. It's still finite, but it's quite small compared to the bandwidth before. Let's say one model that you can do with tight binding presents basically around 3 milli electron volt bandwidth for the region which has a large density of states. The sort of just the toy model for this flat band formation is here. So you consider this sort of twisted reciprocal lattices. So which and then let's look at this vector kind of connecting these two reciprocal lattices. And as a function of this vector, you can find in an uncoupled case two Dirac points. So the red and blue one, which correspond to the two layers. And now if you put a coupling, then all crossings try to become sort of avoided crossings. So like what happens in the C here, and the size of the sort of this avoided crossing is fixed by the interlayer coupling, but the distance between these K points is fixed by the twisting angle. So you can then find sort of a certain magic angle where this avoided crossing size is exactly the size of this sort of distance to the next level. And this is basically the magic angle. And this work has been already mentioned several times here. So there was work by Herrera and others. And then later, after this work, of course, several other works where they found superconductivity and also other types of correlated states in this twisted bilayer graphene. So we studied sort of, Päivi already mentioned some of these our studies on this system, but we studied also this mean field model. And one thing to notice here is that also here superconductivity would be actually inhomogeneous. So sort of localized strongly on on certain parts of this system, and this is basically because of the nature of the flat band eigenstates in this system. So this delta follows basically those. And sort of based on this BKT temperature studies and others, and comparing them to the experiments, first of all, can state that this is consistent with electron phonon mediated superconductivity. At least many of the studies link towards it. It is not for certain yet whether electron phonon is the sort of origin of the interaction, but nevertheless. And another thing is that what we can find out is that the size of the measured BKT temperature points out that actually this is in a regime where this is kind of intermediate between narrow band and flat band limits. So basically, in order to understand the any mean field property, any measurable property of the system, you have to you cannot expand around the Fermi-surface, but actually have to take into account the entire flat band for this property. Okay, so this is my kind of summary slide. I have presented to you three sort of ways of making flat bands from graphene. They all have slightly different scaling size of the flat band, which also matters for the critical temperature of superconductivity. And for the last one, this bilayer graphene, the size of the flat band is actually the size of the superlattice Brillouin zone. The superlattice Brillouin zone is equal to the sort of graphene Brillouin zone divided by the number of unit cells that go into the sort of superlattice. And like already also Päivi mentioned, this n is actually 10,000 at the magic angle, which means that the size of the flat band is quite small. Nevertheless, the TC is a few Kelvin. So sort of if you believe this simple scaling, you would claim that if you would be able to make in such crystalline graphene a flat band of the order of the original sort of Brillouin zone, the critical temperature would be huge. Okay, maybe this is a good point to stop. Thank you for your attention.
Okay, yeah, thanks a lot for the nice talk. And so now is time for questions. Okay, I do not see any yet, so as usual, I will start. This is a very, very naive question about actually strained graphene and bilayer graphene. In both cases, I guess you can also take other lattices, not necessarily graphene. Well, say you can take, say, square lattice and twist it. Or
are you now talking about straining or twisting?
Twisting. For concreteness, let's talk about twisting. So I'm just curious if you replace graphene by, say, square lattice or triangular lattice, or perhaps any other lattice, how would the result change? Because I think people identified magic angles there as well, though maybe that's just my memory deceiving me.
Yeah, I would say that at least this is my guiding sort of view onto this. So in order to have this sort of magic angle and flat band, you need to start with sort of something that has a dispersion like this. So in this case, we have Dirac dispersion. So if you would have something that's
well, Kagoma, for example.
Sorry?
For example, Kagoma, I think that one, it has a flat band, but the touching there, if I remember correctly, is linear.
Yeah, I'm pretty sure that you could do the same actually with other types of lattices, but maybe yeah, it depends on details. So you also are sort of need to care about where the Fermi energy lies. So the good thing about graphene is that sort of in the neutral case, the Fermi energy is at the band touching point. So you don't need to do anything extra to go to this band touching point. And in some other systems, you have to dope it a lot to kind of even reach the flat band. So
okay, but I mean, at least if one looks from the theoretical side, you don't expect any. I mean, you think similar phenomenology would emerge?
In principle, yes. Yeah.
Okay. Thanks. So Päivi, you can unmute yourself.
Yes. So very nice talk, Tero. I have a question about the rhombohedral stacking 3-layer graphene that you mentioned, the experiment. And I know that in your theory, when you had this rhombohedral stack, you got only surface superconductivity. And then, of course, if there are just 3 layers, it's hard to say whether it's surface or not. But
not really. I mean, there are okay, 3 layers.
So are you sure that they have a surface superconductivity, or what would be the difference between the bulk and surface superconductivities here?
I think exactly that sort of characteristics can be revealed by studying this dependence on the electric field, like they have done. So let me point. So I mean, they have 3 layers, and you can kind of imagine that you control the potential on all these 3 layers separately.
Yeah.
And what they have done is basically what actually in their case is that there's a D, which is the difference between these 2 potentials, and then there is this NE, which is the overall charge density, which depends on the average potential. So by studying, so my claim here is that if you can show that whatever you measure depends only sort of on the one of the chemical potentials, it's a slight indication of the fact that it's kind of localized superconductivity. In this case, of course, it's not completely localized, but my point is that the delta would be somewhat larger on these surfaces than the center.
Yeah, and that's what they have seen. You are saying that it's.
I doubt they can directly measure the delta at different layers. They can only measure the total resistance. So
But can they vary 1 mu at a time?
Yes, they can vary 1 mu at a time, and what they see is, I mean, this is basically what is done in the left here, and they show the resistance or resistivity sort of as a function of these 2 parameters. So this is basically proportional to the total mu, and this is my claim is that in order for this to be valid, this depends only on this mu plus minus d. You have to have this kind of sort of dependence, that it depends only on the sum or difference. Okay, and maybe and I think this is consistent with that. But that's the only thing that I can state at the moment about it. So
yeah. Okay, and have you modeled this in detail?
Last week, yes.
Okay.
this is rather I didn't know about it before, and okay, we started earlier, but last week we got some sort of more results about it. So
yeah, very nice. Thanks.
Okay, so Bomjung, please unmute yourself.
Okay, thank you. Thank you for the very nice talk. So my question is about your conclusion page, actually. You showed that the size of the flat pan is different for 3 different cases, right? What's the difference between these 3 systems? Why the size of the flat pan takes a different form?
Sorry, can you repeat?
It's here that you show that the size of the flat pan takes the three different forms, right? Depending on the system. So why you see such a difference? Is there a simple way to explain all of them in a simple way?
I mean, every single sort of the mechanism of flat band formation is different in all 3 cases, and the parameters that go into the size of the flat band are related with the mechanism of the flat band formation. So for example, this case here, the size is determined by the size of the sort of interlayer coupling gamma 1. This is gamma 1. Vf is of course just the regular intralayer Fermi velocity. In this case, the idea is that the pseudo vector potential is has the form beta over L times cosine x over L, basically, or I guess there is a 2 pi here. So and in this case, sort of, it's these parameters that the amplitude of the strain modulation and the period of strain modulation that goes with the size of the flat band that determine it.
Sorry. In the first case, the size of the flat band means so you assume the part of the band has to take the flat form. I mean, what's the meaning of this form?
Okay. So compared to the previous talks in the meeting, it's indeed different. So this is not an isolated flat band. What happens rather is that let's say the energy as a function of momentum, it does this, that it's essentially 0 up to some sort of cutoff, and then it sort of becomes finite. And this cutoff here is what I call the flat band radius. So this, if you look at a 2D dependence, it's a circle, and the flat band radius is gamma 1 divided by the f.
Okay.
Yeah, and that's why it's pi times the radius squared is flat band size.
I see. Maybe for the other 2 cases, also the physics is basically the same, right? In the case of spiral graphene, you assume the band is
comes from the superlattice. Yeah, it comes from the superlattice, but slightly differently. So in this case, it comes from the this is basically a lambda level. The flat band is a lambda level of this pseudo vector potential, but we consider, rather than considering a constant the pseudomagnetic field, like people usually do, we actually look at the periodic sort of pseudomagnetic field. So in reality, the periodic pseudomagnetic field is much easier to realize than constant, because actually constant that does not work. You have to actually infinitely sort of extend your system. It only works for some finite region, this constant magnetic field. But okay, but the Landau level picture is still sort of useful to think about. In the twisted bilayer graphene, it's this sort of avoided crossing between two Dirac points, which is how I explain it.
Okay.
So in this sense, all these approaches have slightly different ways of explaining the size of the flat band. In the twisted bilayer graphene, the flat band seems to be isolated from the other bands. In these two other cases, like in here, you kind of continue with the dispersive band. There are other bands are sort of here. So this is kind of isolated, but it is not entire flat band everywhere. Yeah, and in this case, it's basically just something like this. So for 1D strain, the dependence on kx and ky are completely different. But in, let's say, as a function of ky, it looks like this in this case. Yeah.
Okay. Thank you very much.
Okay.
Yeah. Okay. Other questions? So, Bomjung, I guess, do you have a question or just the hand is still raised? Okay.
Yeah. So I actually plan to talk about this topological insulator part. So if anybody is interested, we can separately discuss it. But one can show that actually there are also flat bands in topological insulators. But
perfect bands or nearly flat?
In the same way as drumheads are sort of nearly flat. So there's a similar kind of that if you have a chiral symmetry in your model, you can have perfect flat bands, but chiral symmetry is not a symmetry of any true lattice, physical lattice. So you can only have approximate in that sense. But they're like drumheads, but they span the entire Brillouin zone. They describe quantized polarization jump.
Okay, so I don't see any raised hands, so I presume then we can conclude this session, and let's thank Tero and all the other speakers of today.